We ventured out into the 100-degree heat in the Arizona desert to create our third ever documentary, this time showing the construction and the operation of one of the world's most advanced manufacturing facilities. Next door to the sprawling construction site is an operational silicon fabrication plant that has secret passageways filled with automated systems designed to transport wafers and other components from point to point. It also has tunnels that bridge the fabs to each other. And even though we all look the same in these dust-free bunny suits, just like in school, everybody knows who the cool kid is. But outside and in the blistering heat, endless cranes slowly bring together one of the USA's biggest technology construction projects, and we were privileged enough to witness a special moment. The whole crew anticipated this one, where one of the single most important heavy-duty facilities was put into place. This entire facility is something that Intel refers to as a mega fab, and it's easy to see why. During all the chaos of touring this overwhelming facility, I realized I need some help to understand what's going on. So Michael Fendrick, engineering manager at Intel, gave us the basics.
Sure, so now that we have the photoresist on there, we have the exposed areas. We may be doing some type of ion implanting. We want to change the properties of that portion.
I don't want to sound like an idiot, but what is ion implanting?
Sure, so it's a semiconductor. I either need to make that region positive or I need to make it negative. Okay. So I got to either implant something with a valence of 3.
And then I realized I need some help to understand the previous help that I needed. So we arranged a technical discussion with an independent technical analyst whom we hold in high regard, David Cantor, to help translate what all of this means and define the processes.
One of the things to keep in mind here is a lot of the issues. It's easy to talk about, oh, we want to make a transistor. And, you know, to a first order approximation, any grad student can make a transistor.
Yes, anyone can make a transistor. We brought you this video and we're self-funding this documentary with our new Factory Tour foil t-shirt. Our Cyberskeleton shirt from our last investigation is shipping now, and following that up, we're taking pre-orders for this custom Factory Tour t-shirt with a brand new ultra shiny blue and silver foil forming a skeletal outline with tools we've seen in factories and fabs from our educational series. The ribcage even has front-opening unified pods, or FOUPs, that are found in silicon fabs around the world, including the one we're touring today. The back features an ultra-shiny foil spine down the center, with surface mount devices that might be found attached by an SMT line. This Intel Fab Tour is a special video for us. As you all know, Gamers Nexus pays for all of its own travel costs and all the costs associated with making this content, meaning we retain complete and total editorial control. It took months of negotiation to get Intel to even agree to those terms, including allowing us to explore parts of the fab that they've never before shown to media. And it took us over a year of collecting all the pieces, interviews, and performing the edits for this documentary, plus all the fact-checking for both independent and Intel engineers. We're able to make all this happen with complete financial independence from the video subject because of your support. Head over to store.gamersnexus.net to help fund our future independently produced documentaries and this one. You can grab one of our brand new Factory Tour shirts, our high heat resistant silicone soldering and project mats, 3D coaster packs, drinkware, and more. Thank you for your support. All this talk of material deposition, ion implanting, photoresists, masks gets incredibly complex, so we need some foundational information, and we're learning right alongside the audience today. We'll start with construction of a fab, since we need one before any silicon-based electronics can even be made. Now it's time to start our journey. When we synchronize the mics and the camera, you gotta clap.
Okay.
But you gotta do it loud.
Okay.
You got to no, I don't know. You got to bring it.
Bam.
All right.
There we go.
That's good.
This is Ron Yun, Senior Construction Project Manager at Intel. He knows a lot about building fabs.
In terms of my role, I'm one of the 4 leaders of the project. In terms of my specific scope domain, I'm over the CSA, the Civil Structural Architectural, as well as the clean room build out for these buildings that you see behind us. So the building, what's actually being built, and then the clean room inside is my responsibility. This is actually a very critical section of the site. Both of these areas that you see, so the area to approximately my 1 o'clock position, that is our batch plant. That's where we make concrete. This area right here, this is a fabrication yard for the truss elements that actually form the roof of the fab building itself.
There are 4 key fab components to discuss today: electricity, water and reclamation, dust filtering in the clean room, and transportation, including for wafers, people, gases, or chemicals. The capacity, distribution, and handling of electricity is critical for a fab. Loss of power can cause hundreds of millions of dollars in damages, even if temporary. In fact, a Samsung fab in Austin, Texas was shut down due to power availability during a Texas freeze previously. This caused an impact to 71,000 wafers. The month-long shutdown cost Samsung between $268 million and $357 million. But for how much power these campuses use, Intel's Ocotillo location used 2 billion kilowatt hours of electricity in 2023. Of these, it self-generated about 11 million kilowatt hours through solar. To handle all of that, Intel needs a special structure installed on its roof, and it takes one of the largest cranes in the world to install. Now, Ron, I want to ask first, when we were walking up here, you saw something going up on a crane. You said, that's a big deal.
Absolutely.
So why was it a big deal? What was it?
That is the E-house. There's only a couple of those that sit on top of the fab building, and the responsibility for those pieces of equipment is to distribute power throughout the fab. Without the power, we have no operating fab. So this is a critical element in order to realize the end state, which is to bake wafers. You're looking at about 150,000 pounds of equipment. So it's a very sizable load. You need a very large crane to place it.
From what I understand, it's actually a somewhat special crane as well.
It's extremely special crane. There's only about 7 of them in the world. This is the Liebherr 13,000, LR 13,000 crane, which has a capacity of 3,000 tons.
Okay.
It's the largest crawler crane in the world, so it moves. So as the site progresses, you move the crane along with it. It rolls on tracks. It's like a track.
And Intel has a special name for that crane. Skyreacher. Your first guess might be that Todd Howard named it, but actually a student at a local school did. And Skyreacher is ginormous. Its 3,000-ton capacity means it could lift about 2,000 porta potties simultaneously. But more realistically, it mostly handles massive structures, like huge truss work, beams, and prefab elements or components like the E-houses. This fab is about 95 feet tall, and given the weight of some of the equipment, the ordinary cranes can't handle it all. But Intel's construction firm, Hoffman Construction, has countless normal cranes on this site as well. Chillers are another heavy piece of equipment. Intel, once again, doesn't like using normal measurements. They say a chiller weighs between 12 and 16 African elephants. Frankly, we're concerned with the obsession with elephants in this industry.
Okay, so 3,000 pounds, ton and a half. So it's not quite an elephant. 4 elephants. 1 GPU.
In a more useful number, that's about 200,000 pounds, or in metric, 4 Stonehenges. Intel also has to deal with water and utilities, and it's not easy with the fab.
We're adjacent to a structure that we call a trestle, which is for conveying utilities and electric power throughout the site.
Okay.
And so that structure is actually currently being built out, and we're on part of the infrastructure in order to facilitate that build out.
The trestle consists of 400 modular trestles, or steel beams, that measure nearly 1.5 miles in length. And what about all of this behind us in the background? So
yeah,
what's going on here?
Yeah, this is part of our expansion. As I mentioned, we've got 4 facilities today. We're adding those 5th and 6th. And as we get to that scale, what you see outside there is a air separation unit. Those towers are part of an air separation unit to allow us to break ambient air to provide our own, nitrogen, oxygen,
Right.
and then use those in the scale we're going to use them on this campus with 6 facilities. Those towers allow for filtration as they, through pressure and temperature, separate air into its composite molecule. In addition to that, we'll be having hydrolyzers that will break down water to produce hydrogen. In order to provide the gases needed or the other facilities, we have a trestle that has to convey these facilities around the campus, because it's just, again, the scale of the campus. It's, again, that dichotomy between the size of everything here and then, our daily process on measure of the transistor.
But water is another consideration. All fabs use a lot of water, whether that's TSMC's, Intel's, or others, to the point that global chip manufacturing should be carefully monitored for its extreme water consumption, especially if you have a fab in your backyard. The water is used throughout the manufacturing process to maintain support systems like scrubbers and cooling towers, and also to clean wafers and maintain a clean environment.
Yeah, we, here in Ocotillo we have 2 facilities. We have one is our quote-unquote water, which allows us to treat and recycle water, and our brine facility, which also allows us to treat and reclaim water with the city of Chandler. The water facility allows us to basically recycle more than 9 million gallons per day of water. And our brine facility on this campus has treated more than 5 billion gallons of water since 1995.
This fab is still years in the making. Michael, do you have any kind of rough timeline you want to set?
No, at this time we're still talking about construction and the 3 to 5 years for completion of this.
You're still in the 3 to 5 years, basically.
We're still within that range.
Can I ask, when did ground break? When did it start?
September 2021.
Okay, cool. Rather than wait the rest of the 3 to 5 years, we just asked if we could go into one of the completed fabs, Fab 42. And that required suiting up. These suits are commonly referred to as bunny suits, and they're necessary to keep dust, skin particles, eyelashes, and hair out of Intel's wafers. Something about a single hair strand potentially causing tens of thousands of dollars of damage, if not more. And because my insurance doesn't cover damage to wafers, I went through half of Intel's hairnet supply. And Ben went through half of the beard net supply. And now that we're dressed up in our formal attire, time to go into the fab.
All right, Steve, let's go into the fab. So we're on about a 2-foot raised metal floor, and we have to keep the fab clean, we have a laminar airflow. The air is flowing from the ceiling straight down, so it's pushing any type of particulates straight down, and it goes through the ventilation system. We actually, to keep this clean room, we filter the air we exchange it about 6 times per minute.
Okay, wow, yeah.
And this main area here these are all the whip stockers. So for all of our product that's not in motion at the time, they're stored in these stocker units right here. And we'll go over to the automated superhighway, so you'll be able to see the overhead hoist vehicles or OHVs.
Is this part of the highway or no?
This is part of the highway, yes. It runs throughout all of the factories, and this is how we transport work in progress or WIP from station to station, tool to tool.
So what actually is stored in these carriers?
And I guess so each of these, so these are again overhead hoist vehicles or OHVs. In there will be carrying a FOUP or front opening unified pod. In that FOUP is one lot or 25 12-inch wafers. Okay. And we consider that one lot.
Our first stop was the fab equivalent of Grand Central Station, including unprecedented media access to the next door FOUP elevator shaft. Before going there though, Michael gave us the breakdown.
So it's called ASH, or the Automated Superhighway. They're always going to be moving to keep them distributed throughout all the factories. So on this particular campus, we have 4 operating factories, Fab 12, 22, 32, and Fab 42. So they're all connected by these automated superhighways, and what it does is it allows us to have flexibility in where we're running WIP. So if I have hot lots are going through and I don't have tools available in this particular factory, great, I can go send it over to another portion of the campus to be produced. So this allows us, instead of having 4 factories, it almost in essence gives us one large mega factory in which we can run, giving us much more flexibility to how much product we can run at a time.
After a simple, can we go into that door over there, and a discussion amongst Intel, we were granted rare access to ascend floors to a gigantic access shaft that feels something like a Star Trek TNG maintenance duct. Immediately upon opening the door from the stairs, we were greeted with this busy interchange of fast-moving robotic FOUPs. Over 20 miles of track exchanged through these buildings, with FOUPs moving on average at 7 miles per hour and carrying up to 25 wafers. This multi-story shaft serves as a gigantic junction of FOUPs getting dispatched to different floors, like down to a subfloor that brings them over to an adjacent and older fab, out to the mile-long Skybridge superhighway connecting all 4 factories, and in the future, more than that, or out to maintenance outposts for regular service. As for why this is so critical to operation, we'll let Michael explain the logistics, this system, and how it works.
There's a couple different layers, depends on what the traffic is. Some of these are high-speed rails over to the other factories. If we have to do maintenance, they actually will come down off the ceiling. But if we have to go to an area where we have some type of corrective maintenance we have to do, they can actually put it off to a different spur so we're not impeding traffic flow. The team has done a great job when it comes to how do we keep the availability and utilization as high as possible on these.
That enables these robotic carriers to take wafers all over the campus and be in equal distribution at all times to maintain smooth operation. But it wasn't always this convenient.
You have to go back to the old days we built fabs. It used to be this one fab, it would just run one technology. We had to package them all up, put them in there, load them into a truck, transport them over, unpackage them, bring it back and forth, and the employees had to do the same thing. I had to de-gown, walk across the parking lot, get my gown back on, and do that. Now, we can walk from the deepest part of Fab 12 all the way to the deepest part of Fab 42. We never have to de-gown, and it's about a mile walk. We had 4-inch, 6-inch, and 8-inch wafers. We weren't in FOUPs, and they were actually boxes, and actually humans carried them around from station to station to station, and they had run cards on there that you literally wrote, and it would have on what's the next operation. I'd pick up that lot box and I'd carry it to the next station and deliver it over there. Wow. And a technician would look on the run card and go, okay, this is the recipe this one needs. Okay, punch it in the tool. The problem is once we got to 12-inch wafers, the amount of potential revenue if I was to fumble this, but also for the amount of clean room space I have over here, the next operation could be 100 yards away. So it doesn't make sense to, at this point, it became more cost efficient to go ahead, overhead hoist vehicles to go do this.
The crazy thing is, none of this is actually where any fabrication happens yet. That is our next stop. A lot of it is top secret too, so you're gonna see some blurring in this video.
The part that I really want to film, we have to edit like where it says.
In fact, we're likely spending weeks of editing time on blurring alone. So grab one of our limited shirts on the store to help fund our editing team. This place is also really, really yellow, so that's better. We're doing our best to color correct, but there's a reason for the yellow. The yellow light is critical anywhere that machines are part of the photolithography process because it eliminates or reduces the amount of shorter wavelength light. Yellow light is about 570 to 580 nanometers in wavelength. The so-called daylight has a broad range and is 400 to 700 nanometers, but the shorter wavelengths in that range will increase the defect rate and reduce yields. But now it gets complicated, so time to introduce the basics of the process. So what's happening
Okay.
here?
So again, when I talk about the main areas in fabrication, there's literally thousands of steps and different processes. But to boil it down to the simplest terms, we have lithography, where we're laying the pattern down onto our wafer or the next layer. And then we have some type of wet etch. It could be a wet etch or a dry etch. And then we're going to have some metal deposition. So this is where we're going to form transistors, where we're forming our interconnects, or forming a type. And then we have planar, where we're going to go ahead and make the area, take the topography off of that area so that we can set up for our next layer. And oversimplifying it, but basically go around and go do the same thing again.
Okay.
And again, that's a very oversimplification, because there's other steps and processes, this and that, to make it. When we ask people is, hey, how long do you think it takes to make wafer? And we get the answers from seconds to minutes to days, week, but the fact of the matter, it actually is measured in months, depending on what type of product or the complexity.
That whole process, when it's in months, does all of that happen in the building it starts in, or does it start?
Yeah, so that part of the process is where we bring in bare silicon wafers into our factory, and so now we purchase these from our supplier, and now where we actually lay down all of our transistors. So the way to think of a semiconductor is we're actually it's a multi-story building. The first story is going to be all of your transistors, and all the subsequent floors are going to be all of your interconnects. This is how you connect all the transistors to each other, and how you get it connected to the outside world. So again, first story is going to be your transistors. Everything else for the next several stories is going to be your interconnects. Cool. So basically, it's the front end of the process and the back end of the process. All those steps are measured in thousands of steps, and it takes, again, over a month to go ahead and make that happen. Again, depending on the complexity of the chip we're manufacturing.
Sure. So we have some terminological basics, but we needed some help to more broadly define what those words actually mean to a fab. How about on the tools side? So give me a top level, some categories of what different types of tools might you find in a fab?
Yeah, absolutely. So, you know, at a high level, you've got deposition and etch, and there's different flavors of those, but deposition is, you know, how do we drop some sort of material on the wafer? Etch, how do we remove it out, right? And, you know, you can combine those two in clever ways to make different patterns. You've got your litho tools, which, you know, I think many people now know about ASML and EUV, and that's typically for, you will have photoresist that will help you make the patterns that you want. You'll expose it with light, and then you will use that to sort of guide your deposition and your etch. And so these tools are often, in many cases, used together.
Photoresist is almost its own entire category, from what I understand as well.
Yeah, different set of chemicals and tools, right? We're looking for something just like, you know, as you would expect, that reacts to light, just like our old film does, in a particular way. Then you've got all sorts of things like cleans. So, you know, everyone, well, maybe not everyone, but, you know, one of the things that people like to talk about is that, you know, a modern fab is way cleaner than any operating room.
Everyone likes to talk about that.
Right.
Literally everybody.
But so part of that is when you're doing things with the wafer, you may need to clean it beforehand, clean it afterwards, get rid of debris, get rid of leftover chemicals. And so cleans are actually super important. Then you've got polishing. So there's some materials that you may not be able to remove with etching. So you instead polish them off. Copper is a quintessential one.
Okay.
And then you would also have ion implantation. So you basically get to shoot ions into a material. Usually you're going to use this for into the silicon to dope it.
Okay.
And then you also would have, there's a broad category of sort of inspection tools, and that's...
So basic quality checking?
Yeah, in some ways, yeah. You want to look at both optically as well as maybe electrically and through other ways, like try to measure ultimately, well, what did I put down? These are super finely honed processes. We want it to be incredibly repeatable, but we also have to check our work.
What is, if you know off the top of your head, generally speaking, what's sort of the life cycle of taking a wafer through a fab? You know, what is, how long is that? What does it look like? We're, I guess, assuming at this point design is done.
Start to finish, a wafer could take, you know, a couple months, 3 months.
Okay.
And there's ways to make it quicker, but, you know, in high volume, when you really want to crank out as many as possible, 2 to 3 months is a good rule of thumb, and it depends on how many times you're passing it through the tools, right? And just as a simple example, if you think about a chip that has 4 metal layers versus 16, it seems like a reasonable assumption one is going to take
Longer than
the other, right? Exactly, right. And so one of the things that has crept up over time is, as the process flows have gotten more complex, we're using more tools, it takes more time, and the fabs get more expensive. So broadly speaking, you're going to start with a silicon wafer, and then you're going to build the transistor, the contact, the fine layers of metal, vias to the next layers of metal, and generally speaking, the metal will be of different sizes, right?
Okay.
And so you're going to have very small wires for data, and then bigger wires for power, right? Like in a lot of the
That makes sense.
right, in a lot of the overclocking, you know, that you've done, right? One of the things is like, what's the resistance of everything getting in? The lower the resistance, the better, right? And those principles are true in, they're just as true of wiring in your house, wires in a motherboard, and wires on chip, right? You know, in some sense, the biggest difference is, you know, when we're sticking wiring in the walls, we're not doing it with multi-million-dollar tools.
Right.
But but a lot of the same principles apply.
Jumping back to the fab, Michael's next step is to start explaining the machines and the processes, and we'll quickly hit some important terms.
And they're going to lay down a photoresist. This is where the masks are, the reticles. We go out there, now we'll take it over to the etching process.
A few definitions and some GN in-house made animations will help make this a lot easier to understand. We'll start with photoresist, photolithography, the reticle, and patterning. The actual logic and circuitry on a wafer is created by using a process of photolithography, wherein light creates a pattern on the surface of the wafer by using photoresists, developer chemicals, masks, and other processes that we'll explain later. As simply as possible, a photoresist is a liquid coating on the wafer. Photoresists are a light-sensitive liquid film that gets applied to the wafer and influences how the light will eventually form the structure of components on the wafer underneath. Photoresists are applied by a process called spin coating, where the film is deposited onto the wafer by spinning the wafer like a disc and depositing the photoresist coating centrally. It then works its way outward, centrifugally. Spin coating is particularly useful because the thickness and consistency of the coating can be controlled by adjusting the angular speed of the spinning, allowing fine-grained control over the resist. This also prevents the liquid from beading up, although additional cleaning steps can be taken to remove uneven excess or bumps like beads that might form in the surface of the resist. This coating is applied in one of the machines that Michael will introduce momentarily. The wafer then gets baked with the resist applied, which eliminates excess and finalizes the coating. Additional coatings of other materials can be applied depending on the use of extreme ultraviolet lithography and the process node. At this stage, the wafer still doesn't have any components for a CPU on it, so this is all just prep, and we've actually left out a lot of steps that we'll be talking about throughout the rest of this video. Resists are positive or negative. A positive photoresist will be weakened by light, which can punch holes through the resist, and is soluble to the developer. You'd want to apply this where you want light to get through. A negative resist will literally resist the etching process and act as a mask against light, becoming insoluble to the developer. Now we turn our attention to photolithography. All right, so we are 100 feet into this room, but there's been a lot of really interesting stuff. Canonically, can you walk me through what's happening here?
Sure, so we're at the photolithography area, and this is the part of the process where we're actually laying the pattern down onto the wafer. So there's two main parts of the photolithography machine. There's the track and there's the scanner. So in the track portion is where we're loading onto the wafers. We're going to do a cleaning step on here to make the surface nice and clean as possible. And they're going to lay down a photoresist. Okay. And this is going to act as kind of like our film that we're using for the process. And as the wafers transfer down, this is where the masks are, the reticles. So the reticle is actually the image that we want to imprint. What is that particular layer we're trying to put down? And this is where we go into the scanner or the camera. So now I have my wafer, I have my photoresist on there, I have my mask or my image, and then I have my light source. At the simplest form, I'm going to illuminate the light. There's portions where the mask is going to reflect back, portions where the light's going to come through. And it's depending on what type of photoresist we're using, in some cases wherever the light shows, it goes. So that portion of the photoresist becomes softer, while the other portions remain hard, so that when we come back out to the developer stage, we go out there, now we'll take it over to the etching process where we're going to go ahead and take off those softer portions of the photoresist so we can get to our next step. We have our photoresist, we've now stripped away those portions. I could be laying down metal layers. So I could be building parts of my transistor, or I could be building my interconnects above that. We could be laying down copper or different type of metals. That portion, I've laid those down. And then I'm going to go to another etch process where I'm going to go ahead and strip away the rest of that photoresist, now exposing the metal that I laid down in portions.
Cool.
So think about it as patterning, segmenting, laying something down or diffusing something in there, and then go ahead and take that area off, and then I'm going to go ahead and go to my next step as well.
Got it. At this point, we had to move along in the fab in order to actually see everything, but we also wanted to continue this conversation and learn more.
And so now you have photoresist covering one portion of the wafer and not covering the other. And so now we have differential access to those two things. So, here we have an example where you can see using multiple immersion lithography steps to try to define, these patterns. And one of the things you'll see is that EUV, it's relatively coarse compared to some of the features we want to make. And so you can see that those lines don't necessarily look perfect. So these two things, those look pretty close. And is it intended that they're close? I don't know, but it looks like, in general, with using EUV, we're able to get them separated a bit. And so, when you asked me about yield earlier, right? Some of these things where you're drawing features and you want them to be separate, one of the ways you can reduce your yield is if you have two things that are supposed to be separate and now they're touching.
Okay.
It's commonly called a bridge. And
why is it that you want to minimize lithography in fabrication?
Yeah, so that's a great question. So first of all, more steps takes more time, right? And then also, of the tools out there, lithography tools tend to be the most expensive single line item. Okay. And then there's a secondary thing, which is kind of gets into some of the almost artistry of this, which is when you're defining a pattern with lithography, you actually have to worry about the mask and the light you're projecting relative to what was there before, right? And you can't line it up perfectly. So you have this issue called overlay, which is, maybe the image you're projecting is a nanometer off from the underlying chip. Well, if you're talking about a large feature like an 800 nanometer wire, well, it's no big deal. 1 nanometer, give or take, between friends, not an issue. When you're talking about 40 nanometers, suddenly, that percentage-wise, it might be significant. And so where you can have multiple sequential steps that are naturally self-aligned, that will, first of all, avoids the lithography step and avoids overlay issues. But you can end up with different challenges along the way.
This place is gigantic. Normally, Intel has a fixed circuit where it takes media and government officials, but we kept asking to go down hallways and corridors that they don't normally show. Intel told us that the fab is about 2% human work and 98% automation, but the human input required is highly specialized and technical. To give some context, our entire tour was about 4 hours, and we're only a few machines in. We need to move on to the next tool. On the way, we passed a lot of airtight storage lockers with tools, warnings of copper contamination so as not to mix things with wafers that may have copper contact, and labels with an acronym we actually recognize. And we asked, but Intel said this machine doesn't listen to My Chemical Romance while it works. The next machine is a behemoth. It looks like a mixture of a submarine hatch and
Literally looks like R2-D2 threw up.
Okay. So where are we now?
Yeah, we're in the metals area. So like we talked earlier, if I was to oversimplify the manufacturing process, we have our patterning, we have some type of etch, and then we have the metals area. So now we're going to lay down some type of metal. It could be copper for interconnects. It could be our copper barrier seed to separate the front end and back of the process. So this is the area where we're actually laying down the metal over here. So this is all going to be done under vacuum because we have some type of chemical reactions going on. And so to prevent unwanted chemical reactions, or in some cases for temperatures we're going to do, we're going to go ahead and do this process under vacuum. So
I don't really know what to ask other than what is going on here.
Sure, so a lot of this stuff you see around here, the main portion in the center is going to be your different process chambers.
Okay.
So my metal I'm laying down over here, but a lot of the support equipment can be some of these are actually your vacuum pumps. So the main portion to get your vacuum is your scroll pump's actually going to be down in the sub-fab.
Okay.
I'm going to go from my ambient down to a sub-temperature. Once I get on here, I need to get down lower in the vacuum. I'm going to have to use a turbomolecular pump to get me to my next range. Then after that, we're going to actually get into cryogenics. We're actually break it down to even lower level. So I'm now vacating.
So you're talking like liquid nitrogen, liquid helium, or?
So in this process here, I'm getting ultra cold. I have carbon in here.
Okay.
So what this part of the process is, since it's so cold, is now the molecules have slowed down. And what they're doing at this point is, I'm not really attracting them to this area. They get into the carbon and they get lost inside of there. So they're moving very slow. So the whole part that I'm looking for is them to go get lost in the carbon here.
Okay.
Here I got oxygen, helium, and I have argon, all kinds of different molecules in here. The problem is my chemical process I'm doing in here, while I'm doing it, I'm now getting unwanted chemical reactions. Right. So to go ahead and get rid of those unwanted chemical reactions, I'm going to go in vacuum and take all those molecules out of the chamber so that I can concentrate on my process being as pure as possible and as efficient as possible.
This whole thing was tough to grasp in a few minutes in the middle of all this chaos, so Intel had an engineer write us a detailed description of the process to share, along with some of our own animations. Intel's engineer wrote this: magnetron sputtering is a physical vapor deposition method, a class of vacuum deposition processes for producing thin films and coatings. The name magnetron sputtering arises from the use of magnetic fields to control the charged ion particles' behavior in the magnetron sputter deposition process. The cryopumps trap molecules such as water vapor, gaseous material, oil, and other substances onto the pump's cold surfaces, effectively freezing them out of the vacuum chamber. Typically, PVD processes are used to deposit films with thicknesses in the range of a few nanometers to thousands of nanometers. However, they can be used to form multi-layer coatings, thick deposits, and freestanding structures. End quote from Intel's engineer. That really helps provide some context to all of this. And since this whole process is effectively invisible to the human eye, that's where the animations came in. This is one of the many processes where there's not a lot of exciting physical movement, but there's a ton of exciting chemical processes happening underneath. And now we get back to the machines in the fab. A lot of this is tubing and wiring, I guess. You said some component of it is coming from the sub-fab, is that right?
So the main fab over here, I have the sub-fab over here. I could have my bulk chemical delivery systems. I could have my RF vacuum generators. I could have my vacuum systems and stuff like that. So instead of taking clean room space for that, because clean room space is precious and expensive, I'm going to have my support equipment in the sub-factory. They're going to run up through the flooring into the system here, so I can maintain the manufactured portions over here. So they're going to run up and down. So again, these areas here are probably, it could be vacuum components, it could be measurement tools of the measure of the vacuum. Also your support for your gases coming in to support if you're trying to inject some type of chemical as part of your process, or striking plasmas and all that. So basically either I'm using it to extract molecules out of my chamber and then to inject whatever my recipe is for how I'm trying to process my wafer.
Perfect, okay. That is a great explanation answering the question of what's going on here, so I appreciate it.
A little less like R2-D2 threw up.
Yes.
Yeah.
Even though many of these machines have been in use for a long time now, it didn't always used to be this advanced.
Very few processes where you see something in motion. That's the way it is. The sensitivity of the processes now is just everything's going to be contained. Like we can talk about later, is we're talking about the wet etch area. It used to be open vats of chemicals with a hood, and you would literally hand dip the wafers in, and you'd have a stopwatch. Oh, this is a 2-minute and 47-second process. Stopwatch. Oh, to the next chemical. Oh, this is a 10-minute process.
Another big change since Michael started his time at Intel has been to the Remote Operations Center.
About 98% of the moves in this factory are actually done by different algorithms and computer systems are making decisions based on, hey, what's the priority going to the factory? What is our drumbeat? What customer commits do we have? And about 2% of the decisions, that these are exceptions, they're going to have to be made by humans. It's actually done in the ROC of the Remote Operations Center.
Okay.
And in some cases, that's actually located outside the factory.
Yes, the Remote Operations Center, and that's not something that Intel normally shows, but we asked, and this is it. These kinds of highly advanced prototypes can't just be shown to anyone. In fact, we'll probably have to blur some of them out, otherwise AMD might catch on to the secrets. Production lots are run from this control center, reducing cleanroom space required and reducing the amount of hassle for employees by keeping the machine commanders in more normal office space. Every wafer run through the Ocotillo site runs through this room first, digitally. Each technician here manages up to 200 tools in the factory, with the highest workstation for tool count managing 1,000. The most challenging station at the fastest pace, and according to Intel, can have as little as 12 seconds of decision-making time per tool per hour if something pops up. These operators have to be sharp. It's like the air traffic control of the fab. The human operators remain necessary for calling the final shots that can dictate where millions of dollars go in the fab. Every room is important, but this room is what gives a digital map of the fab to keep it running. And now, having seen the rock, it's time to get back down to the floor. We've been in this labyrinth for over 2 hours now, and even our hosts sometimes get turned around in this maze.
I have to remember. And so Fab 22, so Fab 42, clean linkway, Fab 32, Fab 22 connected right to it, clean linkway, Fab 12.
Where are we in right now?
Fab 32.
Oh.
And with so much to see, we just sort of walked around for a while and talked about stuff. So what's on either side of us here?
We're in the...
So we're walking... What is this? So where are we going? So where are we we're going from 42.
Is it usually like that? The different...
I haven't brought you over here before.
I was going to say, I think this is
So we're not in the lithography area anymore, areas where we have
turn around.
wafers that haven't been developed. Part of the wet etch area. So again, we talk about one of the main portions, we're either doing a dry etch or a wet etch. These are the wet etch tools. Walk into the link, the clean link between Fab 42 and Fab 32. We're still in the clean room. These are more stockers.
Okay, all right.
Wafer stockers.
Yeah.
So now we're walking from Fab 42 over to the part of the link that connects Fab 42 to Fab 32. And like I said, that the height of Fab 42 and Fab 32 are different because we had made a decision on construction to make it cheaper for construction. We didn't dig down as far. And so that's why the Fab floors are a different level. So we transitioned in through the linkway. We had to go through the stairs to get to the other level. So we're at the level of where the other factory is. It could be a mile walk from the deepest portion of one factory to the other.
With all the meandering done, we're finally on our way to some of our last machines we're gonna get detail on for this particular tour. The vertical diffusion furnace and ion implanting. There's still a little bit of a walk to get over there though, so more opportunity to learn. Non-copper planar, copper planar. So there's more
so
of
this is planar hard. We're doing head rebuilds of the planar area. They have the heads that are doing the chemical, mechanical polish. So this is the rebuild area where we have technicians who are rebuilding that. Again, no different than doing maintenance on your car.
Right.
And again, we don't want to have that in the proper area of the fab. I want to maintain that space so I can increase the amount of production tools I have in there. So we'll transfer some of the supplement type items that still need to be in the clean room. We'll bring them down here.
Right, okay.
In fact, we go to here, this is actually the other fab right here. I have to remember, when I go into the factory, I literally have to, especially at the elevator, I have to remember, am I going to the second floor? Am I going to the third floor?
Right.
Which factory am I in right now?
And now we get to see the vertical diffusion furnaces. Equipment manufacturer ASM says this about diffusion furnaces, quote, "Diffusion is the family of processes that is used exclusively in vertical furnaces to change the composition of silicon by diffusing atoms from the vapor phase into the material that needs to be modified. It is typically used to electrically activate impurities introduced by ion implantation. It can also be designed to drive dopants deeper into a film layer," end quote. That gives us the basics. Let's check back in with Michael for the practical implementation at Intel. Okay, can we get this as the background? You said it's moved from horizontal diffusion.
So,
and you have some
so
stories
I was
about
talking
that.
about the old days. So when my dad was working in the industry, there were horizontal furnaces, and again, the idea of, hey, heat rises. How do I keep my heat and my chemical reaction stable? So that's what I had them. The problem is that the footprint of a fab is extremely expensive.
Right.
So how do I reduce the footprint? So the challenge is, hey, how do I reduce this? Well, the easy answer was go from horizontal to vertical. So this is a vertical diffusion furnace, and upon telling my dad about it, he's like, no, son, I think you're mistaken here. We're talking about horizontal. No, Dad, we fixed that whole problem here.
Yeah.
So this is a vertical diffusion furnaces. We can keep the stable temperature profile for whatever recipe we're running in here. Keeps the footprint of my tool smaller so that I don't have to build my factories as large, or I can dedicate putting more equipment to go get that healthy appetite for chips and get them out. The vertical diffusion furnaces over here. So one of the simplest areas when we first get in the raw wafers, we're going to grow a layer of silicon dioxide onto the wafer as that prep, so we can start building transistors and all that.
Okay.
This will be the main process over here. So this is one of the portions where we're actually going to be loading multiple FOUPs in here, and we're going to be processing multiple lots at the same time. They're going to get transferred into a quartz boat where the wafers get in there, and then they actually go into a quartz tube.
Okay.
Because of the high temperature we're running in here. It's extremely hot at this point.
Quartz as in the stone?
Yeah.
Okay.
So it's going to be a clear quartz on here. And so we could be spraying some type of liquid chemical to grow our silicon dioxide layer. So I'm going to sacrifice some of my silicon at the top to grow silicon dioxide to form my base layer to start building my transistors or my structure in here.
I think this is a fun opportunity too to talk about a little bit of the older day stuff. So you mentioned one of the tools, very advanced tool, stick with notches on it.
So my dad was telling me back in the days when he was doing diffusion, literally they'd have a wooden stick with notches depending on what recipe they're running, and this would tell him how far does he need to put the wafers into the furnace. Oh yeah, got to that notch, and they were lighting it with a Bic lighter, and I'm like, we've gotten a lot more advanced than that in these days.
Very long way to, not only vertical, I haven't seen one Bic lighter here. After the pity laugh from Intel, we brought these questions back to David Cantor to ask more about the vertical diffusion process. What is the application here? I mean, are you effectively baking wafers after steps?
Yeah, so a bunch of things will need to happen at different temperatures. And this actually gets into like one of the more subtle things, which is thermal budget. Generally speaking, you're going to use the hottest temperatures in the front end of the process when you're forming the transistor. And part of this is because if you go back and heat the thing up too bad, you will ruin those transistors, right? And so one of the tricks is, as we're applying metal layers later on, we're going to need to heat things up to fairly warm temperatures for a human, but potentially low for some of these materials. So 100, 200 C are temperatures you might be thinking about for the back end of a process. Sort of the key point here is that if we're laying down copper or some other material, right, it might need to be done at a certain temperature in order to ensure uniformity and proper adhesion, proper spreading, the right set of properties. And so all these processes are temperature dependent, so you've got to dial them in at the right temperature, right? And one of the challenges in the material selection is that different materials have different reactions at different temperatures. And so you need to keep that in mind, because like I said, you can't apply a really high temperature at the late stage of a process, or you wreck everything that came behind it.
This was also a great time to talk about ion implanting, which had come up a number of times at the Intel Fab, but we were never able to dedicate a ton of time to.
Right here we have Intel's FinFET transistor, right, which they debuted in the 22 nanometer process way back in 2011. Right, and this was the first big change from the planar transistor that was, you know, basically what we've been using since I think the 70s, into the third dimension. So there's a lot of moving parts here. You have the source and the drain. Those are parts of silicon that are doped in a particular way. And so, you know, typically this is accomplished through ion implantation. Right.
When you talk about silicon being doped, I'm familiar with the phrase doping from cycling races.
Yes, that's right.
From the Olympics.
Yes.
What does it mean here?
Yeah, no,
Does it make it super strong?
Yes. So what you do is you start getting horse testosterone, and no. So right. So the first thing is, you know, by default, so silicon itself is a substrate, and so you're going to get your silicon wafer. But then what you want to do is, in the silicon wafer, you want to build regions that are positively charged or negatively charged. And you do that via a process called doping. And so what you'll do is you will inject some other element, some ions, to help manipulate the balance of charge in that region. And so, you know, the other thing you might do is you might actually manipulate the temperature of the wafer, and the higher the temperature, the more things will spread out, right? And so that can actually be sometimes a good thing, because the heating will cause things to spread more uniformly. But if they diffuse too much, you know, you sort of don't have a well-defined region anymore. It's going to be in a relatively earlier stage of in the transistor formation process.
Okay.
Now, and it might be used other places, but that's where I certainly know it's used.
Okay.
We've got, you know, our source and our drain, which are, you know, different polarities. And then you have the transistor channel between them. And in the classic planar transistor, you just control the channel with, you know, a gate that is on top of it, right? And so what's different in the FinFET is we now have the transistor channel between the source and the drain, and we're wrapping it on 3 sides. And so, you know, one of the things that was introduced at the 45 nanometer node was high-K gate dielectrics, and in a process called high-K metal gates. And so you would have a metal gate with a high-K dielectric, and the dielectric, that's bad.
Well, California's power grid has struck again, so we took this back outside for a little more conversation, and somehow the sun came back up. Walking through this fab and knowing that these construction projects can cost upwards of $20 billion, one underpinning question we've had has been about time. With David and Michael both telling us it can take 3 months to complete a wafer, we were curious how much of this is a business decision versus a technical one. David got into that. I'm looking for why can't they make it faster?
So, okay, it turns out actually you can, and there's something that actually has been talked about recently, is if you are willing to, you can idle a lot of tools if you have a really important set of wafers to get through.
Okay.
Right, and so this is something that's called a hot lot. And so what you will do is you will like literally say, okay, you know, I'm doing deposition right now, I'm going to do etch next. Let's make sure that etch tool is totally empty and ready to go to minimize latency, right? But now then your etch tool is just kind of sitting there.
It's not getting max value.
Right, and so this is actually one of those things that gets into sort of the underlying economics, which is a lot of this equipment is really expensive, and so if it's underutilized, that's a problem. Okay. And so some of what is going on is there's a trade-off at the macro level of what is the throughput I get out of the fab versus the latency of any one item. So that's like a high level thing, right? So there might be delays here and there, but then the other thing is a lot of these are chemical reactions that can take a certain amount of time. You may also need to manipulate the temperature of the wafer, let it cool down, warm up. There's a lot of subtle things that can happen in there. And then, you know, especially some of the newer tools like EUV machines take a very long time for an individual step. Okay. The more steps you have, there's both the time the step takes, there's time to move the wafer around between tools and potentially stage and wait and transition between those steps. So it can get pretty complicated.
This gives us a new appreciation for the level of technology required to even make a CPU or a GPU. Variations of this process apply to Intel's competitors and peers as well. And although there may be some specific differences to approach, the point remains that being able to even make these devices seems only 1 or 2 steps removed from being impossible. The right people, the right advancements, and the right time all lined up to enable all of this. We have over 3 hours of cut interview footage from David, Michael, Matt, and Ron at Intel, so we'll have to come back to this discussion another time. Likely in some fully separate videos on the channel or on extras, because we spoke with Cantor for over an hour alone, not to mention all of the extras from the tour itself, and we can't fit all of this into just this video. What's even crazier is that this mega fab isn't even the whole process. They can't actually complete a CPU from the literal start to the literal end here. There are ingot suppliers before this. There's people who have to harvest the material components from the earth. And then there's the stages of putting the CPU silicon into its packaging. And we're not talking about the cardboard box, but entire other similarly advanced facilities where the final CPU product is actually put together and finished as something you can socket into a board. And of course, even the more traditional packing plants would be another stage still. Maybe that's a future content piece or a series of them. And if you're interested in more traditional manufacturing, we have an entire playlist of tours, ranging from how screws and cardboard boxes are made, all the way up to AMD's lab tour, and now a fab tour. We walked into this facility knowing absolutely nothing about this process. This is one of those videos where we're not experts, so instead, we deferred to those who we think are. But even those we spoke with in this video probably wouldn't assign themselves the label of expert, because we've noticed a lot of humility every step of the way from those we do view as experts, and it makes sense why. Silicon fabrication is an unbelievably complicated field, and it's impossible that any one human could know every single necessary detail of this process. Even this video doesn't answer the question fully of how a CPU is made. Instead, it combines some of the steps with a walkthrough.
And the truth is, for a lot of these processes, you may know it at a high level, but actually knowing, you know, all of the steps is frankly a trade secret that very few people know. You know, and a lot of people might know about one area that they work in. But knowing how everything fits together is, especially in a modern fab, is really.
It also seems impossibly complex for one person. But.
Yeah, but you know, obviously, you know, there are also like academic institutions where they're doing, you know, IMAC or various universities where they're fabbing chips. They just might, you know, have much fewer metal layers or may only be trying to fabricate a particular structure to prove a point, as opposed to let's do full production at scale with high volume.
And advanced products.
Yeah, exactly.
When we were finishing our tour after 2 days of non-stop questions about specifics of tools, we wanted to fulfill a long-time audience request. Many of you have asked us how to get into this industry, this line of work, and so we asked Michael and Matt about some of where they started and what advice they have. Michael first started at Intel 33 years ago and worked as a repair technician fixing spin motors, RF generators, and doing maintenance internally. He also made databases for Intel. Michael has since worked his way up to being an engineering manager, and Matt started at Intel a few decades ago as well, also in engineering and technician trades. We'll check back in with them one last time for some advice for those who may want to get a job in this field. The number one question we get after something where we get to see really hands-on what do people actually do making this stuff is, how do I get into that kind of field? So whether that's what do you study or what do you do as a profession?
Yeah, a great question. Within the fab itself, we have a big concentration of engineers as well as technicians. And engineers maybe will have a range of degrees from material science, chemistry, physics, mechanical engineering, like myself. In addition, the technicians will have associate degrees. Maybe they've also have skills that they gained through the Air Force or through the armed services. And so we have a broad mix of those technical skills in the facility, whether we're working on the process tools, operating the tools, or solving some of the engineering problems. But as you look across the campus, it gets even larger because you think about the facilities required to operate. We have a number of engineers with civil backgrounds and other mechanical engineering, computer science.
Even just maintaining, I mean, I would imagine Intel probably is big enough to need its own electricians or...
Yeah, we have people with electrical backgrounds because, as an example with our growth, we're going to move from being supplied with 69 kilovolt electricity to 230 kilovolt electricity. We're going to be one of the few commercial users of 230 kV electricity here in Arizona. So it's quite an exciting transition and scale for us.
Yeah, massive scale. And thank you for joining me and for the walkthrough.
Yeah, hope you enjoyed.
Absolutely. I mean, do you have any general advice for people watching?
Sure.
Making those decisions?
So the two main jobs in here is manufacturing technicians. So we're looking for generally people with a 2-year electronics degree, military equivalent experience. What I'm looking for is hand tool aptitude. We're doing preventative corrective maintenance. Do I know how to use hand tools? Do I have critical problem solving skills? Now I'm doing this, can I intelligently think my way through working through this problem? Can I follow specifications? Because our process is so precise, we need to follow those instructions, But then the other portion is being innovative. We don't want our folks to be robots. We want them thinking, hey, you know what? I have a better way that we can go get that done. Let's do an experiment to get that done. So that's on the technician side. From the engineering side, again, any of our hard engineering, mechanical engineering, electrical engineering, material science, and again, looking for that discipline within that engineering field, but also, again, having those problem-solving skills. We are manufacturing the most complex thing invented by humans.
Right.
So we're running to tolerance of things that are, hundreds or thousands times smaller than a human hair. So we're running into problems you can't see. So also is, do you know how to collect data? To one, see what the problem is, but the other part is, can you articulate that to engineering and management, the factory managers, that I know what that problem is. I'm using model-based problem solving. These are my models, and this is the experiment I'd like to go try. So again, is that problem-solving mentality and that innovation is critically important, either for a technician or an engineer.
That's awesome. Awesome advice for anyone in our audience wondering. I think that's about the most direct answer you can get from someone at Intel. So, well, thank you for joining me for the tour.
It's my pleasure. Thank you very much, Steve.
Absolutely. And that's it for this Fab Tour documentary. This is by no means comprehensive, but that's exciting to us, because that means there are a lot more steps we can learn about and we can film, and maybe we can one day make a mega documentary to cover the multiple mega fabs. Thank you sincerely for watching. If you've made it this far, this has been a labor of love project for us, and please consider strongly supporting this video by buying one of our limited edition factory tour foil t-shirts on the GN store. These were just added, and we're taking pre-orders now, and they're a part of our Cyberskeleton series, except this time with the manufacturing tools as part of the skeletal outline. You can even find some foops in the ribcage. These items were made to directly fund this video. This one has been an on and off project in production for a year now, and your support means we can keep making these. We don't take money from these companies when we visit their factories, and we also pay for all of our own travel. So that funding comes from the audience, from you all. As a closing note, our sincere gratitude for the many experts who brought us from knowing nothing to knowing still nothing, actually, but we have a few fancy sounding keywords now, like Photoresist, so that'll at least sound impressive. In particular, we'd like to thank all of those in the industry who are engineers at Intel or outside of Intel who've helped us with fact-checking on this video and getting the details as right as we can. This series was an incredible journey, and we're excited to learn more about this mystifying process in the next one. Subscribe for more, and we'll see you all next time.